Without further ado, Peter van Keken is going to give the keynote speech on mantle convection. I'll give you a 5-minute and a 2-minute warning.
Thank you, Gareth. It sounds imposing, 1,000 computers watching you, but I have a Gmail account, and I'm certain that many more computers than that are watching me, my every move every day. So, let's not start on Facebook. I changed the title of the talk just marginally to reflect better the content after yesterday's great presentations. I want to thank the conveners for inviting me. It's a great pleasure to be at this great celebration of the birth of plate tectonics, or the theory thereof. I want to go back in time a little bit after Tony's great presentation to add a few more historical notes that I think highlighted the important role of, or the discovery of mantle convection. And then we'll jump straight into subduction zone thermal structure and a couple of applications thereof. So we already heard about Holmes, and I was delighted to hear that Holmes gave his presentation on a mechanistic explanation for Wegener's continental drift in this building. Makes me much happier than just being across from Fortnum and Mason. It's just nice to hear history reverberate in these halls. Holmes, of course, provided what we now know as a basic mantle convection underlying plate tectonics. He never formulated plate tectonics itself, but to this day we still have a big issue with understanding how mantle convection and plate tectonics are truly coupled, and why plate tectonics seems to be operating on Earth, but not on any of the other Earth-like planets or satellites that we know of. Veining Minus can be somewhat be considered as a distant academic grandfather of mine. He developed very accurate pendulums to measure, or pendulums to very accurately measure gravity, and he applied that in submarines across the Indonesian archipelago and found massive mass deficits, and from that he derived that there had to be trenches. And this was the first observational evidence for the existence of trenches, what now we know is an integral part of plate tectonics. An important paper that wasn't mentioned yesterday, but I'd like to highlight, is by Griggs. He's an American mineral physicist who tried to convince his readers that the Earth, even though by seismological properties it looks like a solid, can deform like a viscous liquid. And he tied very nicely together Wegener and Holmes and Veining Minus in essentially what is a modern view of mantle convection. That was in 1939, and so it took quite a while to really put the plate tectonics on top and to get us going on the understanding that the Earth is deforming over geologic time throughout the Earth's mantle. Last little bit that was known at the time was the deep seismicity below Japan. It was discovered by Wadachi, the Wadachi from the Wadachi-Benioff zones. Benioff did this after the war. Both of them identified deep seismic belts in the places where the trenches are. And this contour diagram is actually not that much different of what we derive from modern seismicity. So I think all the elements to understand that mantle convection was operating was available to us before the start of the Second World War. Subduction zones have gotten a lot more complicated, and often we like to just start with a little cartoon. Here are some particularly sketches of the deformation mechanisms that decouples the overriding plate from the subducting slab. Of course, there's the seismogenic zone with the large underthrusting events. They typically rupture down to about 35 to 40 kilometers. They typically end at the moho of the overriding plate. The slab is decoupled further along an aseismic extension of the seismogenic zone down to a depth of about 80 kilometers or thereabouts. And that's when the slab gets in contact with the overlying mantle wedge. It starts getting hot, and we start seeing metamorphic dehydration reactions. We start seeing melt forming, and that's where essentially the subduction factory starts. We've also discovered in the last 10 to 12 years or so that in the forearc, due to extensional faulting, fluids are actually actively driven into the crust and into the mantle, serpentinizing the mantle below the slab, causing an excess source of fluid to go down into subduction zones. Somewhat more on the processes of what's happening as far as the fluids is concerned, and the the melting processes that occur. Due to the increased pressure and temperature, metamorphic dehydration reactions happen, which drive off fluids into the overlying mantle wedge. The mantle wedge itself, since it's coupled down below depths of about 80 kilometers, it draws in hot material continuously. And you set up a very nice conveyor belt system where you bring in hot material down to close to where the slab is. That's where the fluids are ingested. And due to the melt point lowering effect of the fluids, you get melting. And that is the principal mechanism by which arc volcanism forms. There's probably a little bit of a role of decompression melting and a little bit of a role of active melting at the slab, although those effects are likely limited. What I would like to discuss in particular today are the cold corner, which is highlighted here, and the causes for intermediate depth seismicity. But first, going back, and Dan has just arrived, so I'm glad that you waited for your entry to show this slide. I'm not welcome at dinner tomorrow. Here's a first model, or one of the first models of the temperature inside a subduction zone. It simply assumes a kinematic slab that goes deep into the mantle. Already the idea of the corner flow, that the slab drives active convection in the overriding mantle wedge, is incorporated. And importantly, it shows that low temperatures in nice non-dimensional units are brought down deeper. Very similar to what we saw in the high Q observations in the 1960s in Tonga. A rather popular code that might have been the first open source code. I don't know how people distributed this, sending punch cards around. Maybe it was just published as an appendix to a JGR paper, and yet undergrads typing it up on the punch cards. But it's a Stux's Minier code, which was a bit simpler. It parameterized the mantle convection in the overriding plate. And I'd like to highlight, my apologies, I'd like to highlight that temperatures in the overriding plate or at the slab surface are incredibly low. Very low compared to what we need to have any type of arc volcanism going. And this was a concern for our people who studied arc volcanoes. They said, well, the arc is hot, and we have this cold stuff going down. So there's a problem, and whenever there's a problem, you invoke heat sources. And a very popular way to do that is to just add shear heating to your models. And this was done by Brody and Brody. We created by just amping up the frictional heating and the shear heating. They caused very high temperatures at the slab surface, and temperatures that, even at present day, we would say are realistic for arcs, except that the mechanism of introducing shear heating violates immediately the first and the second law of thermodynamics in these type of kinematic models. It really should not be done without any careful consideration. And even though you create arc volcanoes this way, it comes at great cost to computational integrity. The cold corner that I highlighted was first seen in heat flow data, particularly in Japan, where a remarkable observation is that outboard in the fore-arc, just before the volcanic front, heat flow values are incredibly depressed. They're among the lowest heat flows that we have on the planet, whereas the volcanic arc is very hot, and therefore heat flows are high. So this cold corner was, I think, first proposed by Tatsumi from this heat flow and from some geochemical arguments, and then brought to models by Satoru Honda. If you do any computational modeling, I would like to point out that the grid resolution, that of course was limited by computational capacity at the time, is likely not quite what you need to resolve the thermal structure. But you do get the major features of the subducting thermal structure, particularly a corner flow that, due to now the inclusion of realistic olivine-style temperature-dependent rheology, actually brings naturally hot temperatures to below the arc and a relatively hot slab surface. You can identify some numerical issues here, and the heat flow goes to zero, which is probably not realistic. But it's a good first order estimate of what the thermal structure looks like in a subduction zone. Furukawa, 25 years ago, was the first to propose that this cold corner forms by decoupling, an extension of the seismogenic zone deeper down. and he identified, based on heat flow arguments that matches his models, that this decoupling should happen at about 70 to 80 kilometers, so that the cold corner extent is down to where the slab is at 70 to 80 kilometers. An influential set of papers, we hear one science paper highlighted, were by Peacock and Wang, and that was in large part because they started tying in the consequences of the thermal models for the mineralogy, dehydration reactions, and the like. They had a finite element model, which I think is the preferred way of resolving the structure of the subducting slab compared to finite difference methods. They have the corner flow, that now looks familiar, cold slab going down. They identified two end members, a very warm subduction that's happening in Nankai, very cold subduction that's happening in Tohoku, where you have old oceanic lithosphere going down fast. And as a consequence, the geotherms are much hotter in southwest Japan and northeast Japan. The band here is for the oceanic crust bracketed by the top of the slab and the moho itself. And you can then put that on metamorphic dehydration reactions and see that the temperatures are not enough to really get close to the solidus or the wet solidus, except in the case of southwest Japan. And so you would predict a little bit of the slab melting only in southwest Japan, not in Tohoku. This was actually a bit of a problem for many arc geochemists because the signature of slab melting or sediment melting is present in all arcs, even in small amounts, but it is there. And so for Tohoku, it was not explained why that was the case. I talked to Simon a year after this when I just started getting interested in subduction zones, and I asked, well, why do you use an isoviscous rheology for the wedge? It's olivine, it's got to be stress dependent, temperature dependent. And he said, well, it's easier to model it this way. And I found it a very honest response. So he said, well, let's try to make it more realistic. And that's what we did in the paper quickly after that, in which we, and apologies for the slightly cluttered graph on the right, I should have cleaned this up. I want to focus on the black and the red models. The black A1 and A2 are the top of the slab and the bottom of the moho in the original Peacock and Wang model. The red are the new moho and top of the slab models that we developed. And the only change we really made was to add realistic rheology for the Mantle wedge. And the consequences of that are rather dramatic. Due to the lower temperature, or the higher temperature, causes lower viscosity. This causes much more efficient advection of hot material to the slab. And as a consequence, the slab surface gets much hotter. So C2 up here actually for Tohoku crosses the wet solidus and is therefore in agreement with the arc geochemistry. And really Simon, Peacock and Wang were close to that, but they just had to switch on the realistic thing. I had lunch with Kellen Wang a little while later, and I asked, well, why did you never look at that? He said, Peter, we did. We switched on the temperature dependence, and it got very hot. We thought it was wrong. I was very happy he never published that, because we could. So I think the top of the slab is hot uniformly across the world. I'll try to demonstrate a little bit further. But because of the cold subduction zones, you can have very strong gradients, and the moho can be a lot colder. So in subductions, you really want to think about the entire crust and uppermost mantle going down, and that they see different pressure and temperature conditions. And that is important consequences for dehydration in the crust. We now know from benchmarks, comparisons between codes, convergence tests, and a variety of other things, that if we have a given set of assumptions about what the subduction zone looks like, we can resolve the thermal structure to within about 1 degree Celsius, as long as we use high enough resolution, and high enough resolution is defined by about 1 kilometer, which is a far cry, of course, of what Honda and others were doing in about 30 years ago. But this is now easy, certainly for 2D models, this is not a problem at all. For 3D models, this is in range, and we can accurately predict these temperatures. That doesn't mean that even though the numerical accuracy is high, that the physical or chemical accuracy is high. The assumptions that go into the model can have large consequences for the actual temperature compared to what you're looking at. And it's a bit of a complicated slide. I will highlight 1 or 2 things out of this. But if you apply a subduction zone model you got to keep in mind that not all models are applicable to your situation. So for example, if you are interested in the last equilibration of melt below the arc, you do not want to use our models because local melt migration increases the temperature at the MOHO significantly. If you want to do back arc spreading, you need to have models that involve that. Temperatures locally can be quite large. 3D flow effects are certainly important, maybe about 100 degree Kelvin, as we try to find out. Certainly the rheology of the mantle wedge itself and how fluids and melt affect that rheology is going to be incredibly important. And there's some big uncertainties because we don't understand that rheology very well. And seismically, it's very hard to image that mantle wedge. And so there's a lot of interdisciplinary work that needs to happen to resolve this. So going through some applications. First, intermediate depth seismicity in relation, or can it be explained by these thermal models? Intermediate depth seismicity to me is defined as below about 40 kilometers depth. That's typically where brittle failure ends. It's a puzzle why earthquakes can occur deeper than that because the confinement pressures are so high. First, we developed a series of models for the global plate tectonic system. We divided the roughly 45,000 kilometer of trench into about 56 segments and made our best estimates of the geometry based on the best available seismicity and forcing parameters. And from that, developed a series of models. I'm just showing you three. Notice that the horizontal axis is different for all of these three models. They certainly don't dip in the same angle into the mantle. Cascadia, over on the left, is one of the hottest subduction zones we have on the planet. I see that the blues go out very quickly. The slab warms up very efficiently. Tohoku is one of the coldest subduction zones we have. You see blues going down to very great depths, and Nicaragua is somewhat in the middle. We can use these thermal models to predict what the petrology is of the subducting slab. In this case, we have the actual geometry of the subducting slab, the same way it was in the previous graph. Then an exploded section where we just exaggerate the vertical depth a little bit. We have an upper crust, lower crust, and mantle. And then we can also predict the water content of this in the same graph. You might not be able to read the legend, but I just want to highlight some transitions: the green schist in green, the blue schist in blue, and then the eclogite in red, with dry eclogite when the austenite goes out in the darker red. Particularly want to highlight, and I've done that with this little black bar here, the blue schist to eclogite transition. Typically, that's a place where you produce a lot of free water. Austenite eclogite still contains a significant amount of water, and only when you get to dry eclogite, it dries out. Notice that before this talk is out, I will stop pushing that forward button when I move to use the laser button. Notice that for Cascadia, we predict that all of the water goes out, and that the only water that is at arc depth, at about 100 kilometers depth, it comes from the peridotite. And there's some good geochemical evidence from the Oregon group that suggests that indeed, from isotope ratios of boron and hydrogen, that is indeed the location where the waters come from. For Nicaragua, we have the ability to recycle water to the deep earth in the Cabros. For Tohoku, we have a lot more, including in the serpentinite, where the antigerite phase goes into phase A, one of those deep dense hydrous silicates. And so, as a side story, you can use these models to predict how much water goes into the interior and then try to figure out what the consequences are for the long-term chemical and thermal evolution of the planet. Back to blue schist to eclogite. It's a major phase change in the oceanic crust. Pretty little eclogite from St. Catalina Island and an eclogite from Norway. This occurs under higher pressure and temperature, or intermediate pressure and temperature, and it produces a lot of fluids. I think those fluids are the reason for the earthquakes. And let me first show you some observational evidence for that. This is a seismic image of the subducting slab below Alaska. It's from receiver functions. It's not mantle tomography, but similarly to tomography, you can interpret this red band as the subducting oceanic crust that is still in basalt. It's still in blue schist phases. It has lower velocities than the surrounding mantle, and therefore it stands out in red. The moho is highlighted here. From that we can infer the top of the slab. The black dots are the earthquakes, which are located within the seismic velocity model based on the seismic array study from Jeff Abers and others that was done in this region. And intriguingly, the earthquakes tend to sit at the top of the oceanic crust and then dip into the oceanic crust as you get deeper down. There are no earthquakes in the mantle below this, and that seems to be a common occurrence for cold or intermediate subduction zones like this one. The little blue line that maybe I should highlight a little bit, this one here is what we predict as the blue schist to eclogite boundary. This is not based, it's not just a fit through the earthquakes, it is our prediction. And so if you're a fan of dehydration and brittlement to explain earthquakes, this is the place to do it, because it looks like the earthquakes are right where the dehydration happens. In Japan, everything is better. There are thousands of earthquakes per year, thousands of seismometers, thousands of seismologists. And the images you get from that, it's incredibly data-rich environment to work in. This is the PhD work by Saeko Kita at Tohoku University. This is a section through the subducting slab below Sendai. And what you see is the inferred top of the slab, which is based on actually topside reflections, and the earthquakes are located with respect to that top of the slab. The absolute position can probably vary a little bit, but the relative position of the earthquakes to the top of the slab are to within a kilometer or less accurate. You see two bands of seismicity. That's the famous double seismic zone. You see seismicity, the top seismicity is primarily confined to the crust. Again, suggesting, similar to Alaska, that there's a petrological reason for the earthquakes here. And then, again, the blue schist line that is sketched in there in blue is not a model. It's actually our prediction for where this blue schist to eclogite transition is. And so this suggests, rather simply, that fluids that are driven off by this reaction will go up to the arc to feed the arc volcanism eventually. But they also go back up to the crust, and that this pulse of fluids can actually cause the earthquakes at depths below where brittle faulting is ruled out. So it's a fluid-related weakening of the crust that allows for the seismicity. We have some model support for this. This is work by Kian Wilson, Mark Spiegelman, and Brad Hacker and I, where we introduced fluid flow in subduction zones, and not just looking at the buoyancy of the fluids or the effects of the dynamic pressure, but also the compaction pressure, which is set up by the compaction of the rock as the fluids leave it. These create important pressure gradients, and the best example, I think, is in the bottom here, where if there's just buoyancy, then the arrows, this is an exploded section of the crust. The fluids that are being produced are just going straight up the slab and out of the slab and just disappear into the mantle wedge. As soon as you add the compaction pressure, the fluids actually have the tendency to stay inside the slab and punched out at the greater depth. We have now also good seismic evidence for this, which is obtained by, again, the Sendai group. Very beautiful work by Sheena and others, where they identified the seismic structure of the downgoing oceanic crust. And they did this by comparing P waves and S waves, and then an intermediate phase that comes in a seismic record between the P and the S waves, which is the PS converted phase that travels as a P wave through the crust and then converts to an S wave. If you have enough earthquakes like this and enough seismic stations, you can actually map out the P wave velocity of the downgoing oceanic crust. That is shown in this image. Again, this is below Sendai in Tohoku, northern Japan. The cross-section is over here, where we see rather low velocities. These are P wave velocities of 6.5 kilometers per second or less. There is no known rock on Earth under those pressures that can have these low P wave velocities as best as we know. And so, to me, this is a clear indication that there are free fluids present at these locations of the extreme low P wave velocity. The larger diagram is a map view that looks down on the top of the subducting slab. The overriding structure is taken off. And you see that the band of low velocity, sometimes it's larger, sometimes it's smaller, but it seems to be present almost everywhere. If you then put the seismicity on top, you actually get a quite nice coverage that most of the seismicity seems to be confined to these very low P wave velocities. Let's do this again. So this to me indicates that we have a rather strong evidence that fluids that are being produced by metamorphic dehydration reactions go back up the slab and trigger seismicity. So this is in essence what's happening in Oklahoma. Thanks to the great efforts of the gas and oil industry, Oklahoma is now the most seismically active of the lower 48 states. Only Alaska is more active than that. And that's all due to the injection of fluids from fracking that causes reduction in confining pressure and therefore earthquakes. I think the same is happening below Japan. I'm just gonna, my second application, I'll be happy to talk to anybody about that. It will take more than the 3 minutes that I have, so I will finish off with this slide, where we look at intermediate depth seismicity in warm subduction zones. And the situation here is intriguingly different. For the cold subduction zones, the seismicity of the upper plane was in the oceanic crust. In warm subduction zones, there are no earthquakes in the crust. The crust is highlighted. This is the moho here with the top of the slab inferred from that. All the earthquakes in Cascadia are within the subducting peridotite or the mantle. Same below Nankai, Tokai section, where again the moho is the solid line. That one is the easiest to infer from seismic tomography or receiver functions. And all the seismicity, again, sits in the mantle wedge. Very strong petrological control on where earthquakes are. In warm subduction zones, they occur in the peridotite. In cold subduction zones, they occur in the crust. I'm not entirely certain whether this is exactly the same, where there's fluids being triggered by dehydration reactions, but I find it intriguing that if I put our predicted antigerite out, so this is where antigerite goes into dry peridotite, or where the antigerite in the peridotite goes, it becomes dry, is again at the down dip limit of the seismicity. So maybe there's a similar story here. I'm going to leave it at that. Thank you for your attention.
Lydia Lonergan, Imperial College. And this may be a very naive question, obviously, for those who work in subduction zones. I work in sort of shallow crust. But I'm curious to know how you envisage this fluid in the subduction zones, in these metamorphic rocks. I mean, is it intergrain melt? And therefore, is it affecting the overall seismic velocity? Whereas, of course, we know in these fracking situations, so it's brittle crust, and we know and we can image the actual oil in between the pores or in microfractures?
That's a great question. It is likely a combination of the various hydrous flow mechanisms that you have. So as soon as the free fluids form, there probably is fracture mechanics, but there could also be just Darcy flow. We don't know for certain because the pressures are sufficiently high that the mechanisms might be different than that for the shallow crust. So that's something that I think the folks who do rock mechanics need to figure out.
Dan McKenzie, you've said quite a lot about the earthquakes down to a depth of about 180 to 200 kilometers, but very little about the ones which happen at in the double seismic zone at the bottom and deeper down beneath Japan. And it's always seemed to me that this has also to be supported by fluid pressure, because you can't otherwise that amount of lithostatic pressure, otherwise you can't slip anything. But I don't know where that water comes from.
Me neither. That's why, and that's why I didn't talk about it.
Time for a final quick question. Thank you very much. So next, Nicky White. We'll be talking about residual oceanic depth at mantle convection. I'll give you 5 and 2 minute warning. Yeah.
I'd like to talk about an issue that's been rumbling away in the undergrowth, both before 1967, during that time period, and very much at the present day. And it really starts with an important paper written in, I think, 1935 by Chaim Pekaris, ironically communicated to the wider world by Harold Jeffreys, who is very much an elephant in this room, I think, during this meeting. So what Pekaris's insight was based on was a number that his friend from down the corridor in MIT came up with. So Norman Haskell was the first person to estimate the viscosity of the mantle using the emergent strand lines in the Scandinavian area. And this is a one-page paper he wrote in, I think, 1935. The number is amazingly robust. It hasn't really changed since those days. So what Pekaris understood in the mid-30s was that if the mantle is viscous as opposed to elastic on long timescales, it means that mass anomalies, mass anomalies which represent deficits within the mantle, slightly paradoxically produce positive, what's called dynamic topography at the Earth's surface, whereas mass excess, in blue here, produce negative dynamic topography. That wouldn't happen if the mantle was purely elastic. Now, the glue the most obvious manifestation of lateral mass anomalies within the mantle is, of course, the geoid, shown here, because the geoid represents an equipotential surface. So once again, the geoid highs and lows here, these geoidal highs in red, and lows in blue, anti-correlate with the large mass anomalies that were identified by seismic tomography starting in the late 1970s. So the analytical glue that holds all this together is the work of Stokes, who's an Irish titan of applied maths from the 19th century, born in Sligo, and buried on the road I cycle along every day, Mill Road in Cambridge. Stokes Flow is basically what's going on, and this is easiest to understand if you think of a ball being dropped through a cylinder full of syrup. So Stokes came up with the expression for the flow velocity, which is related to little g, obviously. It's also related to the density difference and to the viscosity of the material. So what people have been then doing is using seismic tomography and the geoid and an elaboration of Stokes's flow to calculate what's called the dynamic topography at the Earth's surface. So this is the component of topography that is maintained by mantle convection, by mass anomalies deep within the Earth. Here are two relatively recent examples, but this topic was really kicked off by Brad Hager and Mark Richards, following on from the work of McKenzie and others in the mid-80s. And the papers of Hager and Richards are still well worth reading. The key thing about these predictions is they predict long wavelength dynamic up and down movements of the Earth's surface with amplitudes of between 1 and 2 kilometers. The question is it actually there? And you might think that is easy to test. It's difficult mostly because of, Tony actually doesn't like this expression and said, I can't use it until he's gone. But what I mean here is that the density variation and the thickness variation within both the continental lithosphere and the oceanic lithosphere make it hard to see through that to a dynamic topographic component. The easiest place to do this is in the oceanic realm. And this is a very easy thing to do. So we're essentially interested in measuring what are called residual depth anomalies with respect to the cooling and deepening ocean floor. Bill Maynard really pioneered this back in the early 70s. It's an easy calculation to do, but at that time and until very recently, there wasn't really enough good observations in the ocean to do this as carefully as we would like. The key observations come from industry, principally the seismic reflection industry, and it's these beautiful, crisp, if slightly boring looking images of ocean floor. Everything's terribly flat. The key thing is you need to be able to see the sedimentary section accurately, because you've got to correct that out in order to obtain these residual depth anomaly measurements. And that's been very difficult to do until really the last 10 years. And you also need to see where the oceanic moho is. So there are two important corrections, a sedimentary correction and a crustal thickness correction. So armed with a lot of data from companies like ION, who are represented here at this meeting, and also looking back in time to this blended trailblazing work of Lamont under Ewing that we talked about yesterday. So you can use that old Ewing data with care, and not all of it, but the best of it. And some of that's shown in the red dots in here. The blue stuff is mostly this industry data. So these are long, high-quality seismic reflection lines that tip out onto old ocean floor, sometimes go way out onto ocean floor. And we can use that information to turn what's shown here into a map of residual depth anomalies, which we interpret. The most reasonable interpretation of these residual depth anomalies is that they represent a dynamic subplate component, basically, of up and down, where red is up, anomalously up, blue is anomalously down. There are some very well-known anomalies that we've known about for a long time on this map, notably the fact that the Argentine abyssal plain is drawn down by between 1 and 2 kilometers. There's a big drawdown between Australia and Antarctica, curiously called the Antarctic Australian Discordance. India is interesting because on one side of India, the ocean floor is anomalously up, and on the other side of India, the ocean floor is anomalously down. And this puts a jaunty tilt on India, which is not flexural. The other things you can see here are Iceland plume, of course, comes out very clearly, and Hawaii as well. So I'm just going to zoom in on two aspects. You'd expect when you're bang up against continental margins, the anomalies I'm showing you here should have some expression on the margin. Well, before taking you onto the African margin, I just want to show you a transect along the length of the West African coastline. So these are the residual depth anomalies we're looking at as a function of distance from essentially the equator at this end down to about South Africa. And this is not noise. These signals oscillations of the old ocean floor by plus or minus 1 kilometre with a wavelength of about 500 to 1,000 kilometres. So we've propagated the errors as carefully as we could. This is one of the places in the world where there's actually a good, you can tune it to the long wavelength gravity. That's not true everywhere, but in this place it works very well. It's amazing. Old ocean floor is meant to be very boring. It's meant to be sitting in isostatic nirvana, to coin another expression, minding its own business. But in fact, it's very bouncy. It's very bouncy indeed. It's going up and down. Of course, there's no temporal information here. This is just a spatial information. I now want to take you into the plain. We're offshore Angola here. So this is an offshore expression of a domal feature on the ocean floor. And if we go onto the shelf, you can see how this is expressed. I'm going to show this fairly quickly. This is a seismic line. You can see bathymetry at the top. There's a multiple that you can ignore. You can see truncated reflections at the top here. These are foreset delta deposits, and amazingly, they're Pliocene in age. So we've stripped off about 0.5 kilometre since the Pliocene here. There's another feature here, which is Oligomycene in age here. So essentially, there's what's called aggradation through to the Oligomycene and then aggradation. So without going into it in detail, this Angolan dome appears to have grown very rapidly in 2 phases, an Oligomycene phase and a much more recent phase. And Richard Walker from Oxford has actually recently shown that the emergent terraces along the Angolan coastline are consistent with this dome growing today at between 1 and 2 millimeters a year, which is amazingly fast. Okay, you can see the opposite effect, a down effect, notably off the northwest shelf of Australia. So this region in here, you can see the residual depth anomalies are all blue on places like the Argos abyssal plain and the Cuvier abyssal plain. So it's old ocean floor that's much deeper than it should be. And if you pop onto the adjacent shelf, what Carol Charnota showed using splendid 3D seismic data from PGS is you can see here it's a Miocene carbonate reef complex. And those of you familiar with sequence stratigraphy will see that there's progradation out to about this point, which is about 10 million years ago, and then very rapid aggradation with what's called carbonate high stand shedding off the top. So we think the reason for this is that we're looking at the growth of stratigraphy into newly available accommodation space. So the whole area sank rapidly, about 10 million years ago, and that allowed for the growth of the carbonate reef. So I'm going to end in the last few minutes by bringing you back to the models. In order to compare our point measurements of residual depth with models, it's not fair, as that community pointed out very clearly to me, simply to put our spot measurements on their beautiful, smooth, spherically, harmonically determined models. So we had to be very brave, and with a lot of help from David Alatar in Cambridge, Mark Hoggard, I and David wove our residual depth anomalies, including constraints on the continents, into a spherical harmonic model, which we can take out to spherical harmonic degree about 30. Now, this looks different to the predictions that I showed at the start. Just to refine that, if we just isolate the degree 2, the longest wavelength component, about 10,000 kilometers or so in length, the degree 2 component of our data set looks like this. This isn't plus or minus 2 kilometers as we see in the predictions. It's more like plus or minus 100 meters. It can't be 0 at the longest degrees. At degree 2 or 3, you do need a small amount of dynamic topography at these wavelengths to be consistent with the geoidal estimates. So it's not 0, but it's certainly not between 1 and 2 kilometers. And what we're saying here is consistent with the recent work of Peter Molnar and others. So to put that in slightly starker terms, you can produce a power spectrum of our observations. So power is simply the amplitude squared of the residual depth as a function of spherical harmonic degree with a wavelength along the top. Our results are in red here. This is satisfactorily consistent with something called Cowley's rule that I don't have time to go into. The key thing is that our red estimates show you that the significant power or dynamic topography at quite short wavelengths, which I think is important and interesting for the future. And critically, at degree 2, at low degree, we see an order of magnitude less power than the predicted models. This means that the models based on Stokes Flow are wrong. They're not a bit wrong, they're completely wrong. And there I will end. The brave new future in this is to try and get better constraints in the continents than we've done hitherto, and also to explore how observed dynamic topography varies through time. The word here, this funny word, was coined by Lester King, who's another elephant in the room. Lester King was a pioneering geomorphologist who worked a lot on Africa. He was actually born in Wimbledon, just down the road. And he saw long wavelength warpings on scales of 500 to 1,000 kilometers that he thought were very youthful across Africa, and he referred to it as cymatogeny, or the undulatory orogeny. And he thought it was something to do with levitating mantle. And I'll stop there.
Nicky, I think at some point you talked about the mantle as a waterbed. And if that's the case, how well do your ops, for example, correlate with zones of seafloor magmatism or on the passive margins? I know the Angolan example has actually onshore magmatism, but is this a regular correlation?
To some extent, yes, yeah. And people have pointed out correlations like that before. I mean, one that springs to mind is the Bermuda swell, which is probably a hotspot. A more important correlation, in a sense, is that there is a reasonable correlation between our results in the oceans and the results of global surface wave tomography. notably the work of people like Keith Priestley and also Schaefer and Lebedev. So there's quite a good correlation. So we think a lot of the residual depth anomalies we're seeing at up to degree 30, so those short wavelengths, correlate well with things happening immediately beneath the plate in the asthenosphere. That's not a new idea, but it's worth it bearing in mind that the asthenosphere and what it contributes is totally excluded from the global dynamic topographic predictions.
Yeah. Isn't that David Rowley, University of Chicago? Isn't that the critical point, that those calculations truncate at 350 kilometers and project all of that dynamic topography as if the upper 350 kilometers was a rigid?
That is absolutely true, but I don't think it's a good thing. And I doubt if you think it's a good thing.
So you can't have short wavelength.
It can't, no.
They can't have it.
But the other thing they can't have is plus or minus 2 kilometers at degree 2. That's not there either.
Of course.
And in fact, the plus or minus 100 meters that we see at degree 2 is entirely consistent with the sensitivity kernels of Hager and Richards, in my view.
Next we have Lara Kalnins from Edinburgh, who's going to be talking about anisotropy in oceanic lithosphere. I'll give you a 5 and a 2 minute one.
Yeah. So Nicky has actually set this up really nicely for me and provided me with a couple of lovely quotes, because essentially what this does is it goes and uses Tony's isostatic tyranny and tries to use it to inspect the strength of the oceanic lithosphere. And when I'm talking about strength, I'm talking about the long-term mechanical strength. And we can actually only measure this when it's been deformed. And conveniently, as Nicky put it, the lithosphere is very bouncy. So when you put something like a mountain on it, it deforms similar to how a trampoline deforms under a person's weight. And then depending on the thickness of the trampoline or the lithosphere, you get different amplitudes and wavelengths to the depression. And that's what we measure, most commonly to do it globally from the relationship between gravity and topography. More locally, if you have it available, you can use seismic or other data. And this is usually measured in terms of the analogy to the thickness of a purely elastic plate, or TE. This is, unsurprisingly, how strong something is quite a key physical parameter in how it behaves. So it influences a wide range of things, from mountain building to long-term sea level change, but it's also influenced by a wide range of things. And so we look at the magnitude of this strength, how it varies laterally and temporally, but something else that can also be important is its directional variation, its anisotropy. Many geological materials and processes are anisotropic, often highly anisotropic, and so that leads to a natural expectation that the resulting strength that's been influenced by all of these processes and materials might also be anisotropic. And I said it's commonly measured by looking at the relationship between gravity and topography, or bathymetry, often with the coherence or admittance. And these spectra, if you look at them, are often anisotropic. So this is a set of 2D coherence spectra. Some of them are very nice, tidy bullseyes. Some of them are not. But the question is, does anisotropic coherence or admittance mean anisotropic strength? And this is something that Frederick Simons and I started working on in the continents. And that was triggered because it had been done by a number of people, but the measurements weren't being very cooperative because they didn't tend to line up with other things you might expect them to. Seismic anisotropy, stress measurements, or sometimes even they didn't agree with each other, which is always a sign of a scientific technique that's working really well. And so we went back and looked at it. There was one paper in particular in 2011 that we both looked at. Frederick looked at it, thought they were getting an awful lot near the margins where they may be picking up anisotropy in the topography. I looked at it and thought the anisotropy was clustering near high gradients in TE. Was the method somehow confusing gradients and isotropic TE with anisotropy? So we went back and said, we'll take a common sort of middle-of-the-road technique and we'll just look at how can we make this robust. And so the first thing we said is, well, the anisotropy should be mathematically significant. And so we look at the azimuthal average, compare it to the overall average coherence, and say you need to have a peak that's high enough to be significantly different, and it needs to have a well-defined direction. You can argue about how wide you want to let it be, but if it's 90 or 100 degrees, you don't really know what directions it's pointing. And then it should be geophysically significant. We're interested in TE, and you often get these patches of anisotropy out at very short wavelengths. I'm sure it's telling us something. I have no idea what it is, but it's not about TE. So the second test is, do the TE estimates from the anisotropy actually fall out with the uncertainty on the isotropic estimate? The third factor is the one that Frederick started with, which is topography and gravity data are often very anisotropic. And the synthetic testing does show that you can get a false positive from this. You can take anisotropic topography, put it on a perfectly isotropic elastic plate, and out comes spurious anisotropy. The problem is that geologically you would often expect them to align. If you have a big mountain belt, the topography is anisotropic, the gravity is anisotropic, you wouldn't be at all surprised to find the lithospheric strength is anisotropic in the same direction. So this is sort of a halfway house. We don't throw them out, we just flag them as being a different color and think about whether it makes sense. So as I said, we started in the continents, we designed our tests, we tested them and calibrated them on synthetic and semi-synthetic data. We ran them over all of the continents, and this happened. Essentially all of the directions disappeared. Virtually nothing was robust. That was quite disappointing. We did at least get it into EPSL, which was a reasonably good consolation prize for having destroyed all of the measurements. But what I noticed was that most of what survived was in the oceans, just sort of the edges of the boxes that we had gone into for computational convenience. And there was even an early hint that it might align with something interesting, because if you know the area, triple junction, and you can see a difference in domain. The oceans are kind of a blind spot for a lot of people, and so no one had actually done it in the oceans at all. So we started going, and these are quite preliminary results. Here's an example from Africa. These are the weak Atlantic and Africa. Weak directions, strong directions. You can see a lot of these do align with topography. That's why they're brown. In the Pacific, well, the first result is there are results that seem to be robust, and that's quite nice, having spent the previous time destroying all of my measurements. Some testing. If you are familiar with TE, you'll know the size of the window you use is very, very important. You can generally get away with smaller in the oceans because it is generally weaker. So some different sizes. Doesn't change too much. The directions are largely consistent across sizes, which means that the smaller windows are generally sound. You do lose some of the fine variations as you go to larger windows. It's still a question whether that's the removal of noise or over-smoothing. The other factor you do see is that the boundaries between domains can shift. Most obviously seen going into the margin of Africa here. As the window gets bigger, the oceanic signal just blurs into the space where there was no robust signal. Another big question in the oceans is, what data sets do you use? Because a lot of bathymetric data contains interpolation based on pixels that are inferred from gravity, or more often from the geoid via gravity. They do use completely different wavelengths. This is on purpose, because if you're estimating the bathymetry, you don't want to have to know what the TE is. But there's still some concerns about, is there an element of circularity there that's problematic? So I tested two bathymetric data sets, one with prediction, one without, and also two gravity data sets. All the results I've shown so far have been using the bathymetry data set with no inferred gravity, so it should be safe. However, the coverage of robust directions varies dramatically. That's what we had before. That's a different pair of data sets. Some pairings have very different coverage between areas, between the Atlantic and the Pacific, and even between weak and strong directions in the same area. The coverage after the mathematical significance testing is similar. It's the geophysical test that's tipping it over. So it may be near a key threshold. Right now it's been calibrated on sort of generic fractal topography or bathymetry. So one of the bits of future work is to use a synthetic test that's optimized for the structure of bathymetry and potentially retune that testing. The good news, though, is that the robust directions where they do survive tend to match across all 4 pairs. And the areas of inconsistent results tend to be removed by the robustness testing, which is good in terms of suggesting it is, in fact, removing things that aren't robust. So enough of the technical side of things. What about the geological possibilities? So again, here's the Atlantic. This is an old version, right. And here's the Pacific. What you might notice, the thing that jumped out to me, is there's a giant hole around Hawaii. You get a little bit of coverage with the weak directions, and you then get the same effect around Cape Verde and the Canaries. You can also see a distinct shift in direction as you go into these continental margins, although not so much tipping onto North America. So it gives a couple of interesting things, that sometimes we see a clear shift at the margin going back to Frederick's original intuition. Sometimes we don't. So that leads an interesting question once I get a little bit farther and set it loose over the entire globe. Is it a generic margin signature that is just, there is of course a gigantic topographic step, or does it actually vary some with margin type? Is it telling us something more interesting? And the other interesting one is around the major intraplate volcanism. Is it something that implies that the anisotropy is lost or changes as the lithosphere grows from underneath versus seafloor spreading? Or is it that, of course, you don't get a large body of intraplate volcanism without altering the lithosphere significantly? Is that enough to reset the anisotropy in some ways? Slightly more subtle thing is this just takes 10 by 10 patches and bins them in roses. And what you can hopefully see through the transparency is that the strong directions largely align ridge parallel. There are a few exceptions, and it is allowed to pick multiple directions, and there are some where it does. Weak directions are a little more complicated. Some of them are very nicely aligned, others are not. And you see similar things in the Pacific. Some very neatly aligned, some not. So a couple of sort of interesting questions. The first order result, that the seafloor spreading has a strong influence, is what you'd expect, and that the strong direction is ridge parallel and the weak direction is cross-cutting the dominant spreading fabric. Why is it variable? What makes it vary? And what about the secondary picks? They seem to tend to come where there's some areas of topography, but not huge topography. Hawaii, as I said, already clears things out. And so that gives a sort of interesting intermediate ground of, do you see something different when you've had moderate volcanism, perhaps not enough to fully reset things, but to see later times, versus the dramatic stuff? And then finally, what about the Mendocino triple junction that started me off? It does survive. There is a different domain, but with slightly more information, we go back to a small plate that's featured quite a lot today. It seems to align with the Wanda Fuca. Thank you.
Questions?
Lara, thanks. Sort of two parts of a question. What depth or thickness is your anisotropy telling us about? And how does it compare with the SKS sort of data that Mantle geophysicists look at?
So it is predominantly sensitive to where the bathymetric signal is coming from and where the gravity signal is coming from. So it is largely a lithosphere integrative measurement. It doesn't have depth sensitivity within that. I have not yet compared it with the seismic anisotropy. That is certainly on the list once I get a global run. Obviously, we hope that it will be tidy. The potential complication is that in areas where there's a time lag in this, because if you're looking at abyssal hills, that signature is largely locked in when it was formed. And it may now be over, things may have changed since it was formed, similarly with the volcanism, so I'll have to try and unpick that time history.
For our final talk of the session, great. John Casey from Houston will be talking about ophiolites. I'll give you a 5 and a 2-minute warning.
Okay. So this talk is co-authored with John Dewey. So we're going to talk about large slab ophiolite complexes, not little pieces subducted into accretionary prisms, and their role in the initiation of subduction and growth of plates and forearcs in particular, and how forearcs and ophiolites correlate. I don't have many historical pictures or slides in this talk, but this is historical. This picture was taken on the backside of the North Arm Massif of the Bay of Islands ophiolite in 1975. Oops. And as I was flying in on a float plane, and I recognized that the tree line was kind of funny. It sort of went up and down with the topography a little bit, and I said, well, what's going on? And so ultimately I mapped all this, and the moon is up here. This is the residual Hartsbergites, where nothing grows except mosquitoes and black flies. And then this was the basal contact, the mantle detachment zone, and that contact was between residual ultramafic rocks and two pyroxene garnet granulites down through amphibolites and green schist, and then into basal melanges and some near the margin seamount complexes that were detached below but unmetamorphosed, and then finally into the relatively unmetamorphosed allochthonous slope rise complex, Flish and melange below. So this was my introduction, my first flight into the Bay of Islands. So just to talk about what got us started on all of this was, and looking at forearcs, was the geometries we saw in the ophiolites. So the structural front of the tectonic allochthons in Newfoundland is right along the front of these ophiolite belts. This is the St. Anthony. This is the Bay of Islands complex. It's about 100 kilometers long and 25 kilometers wide. It has great exposures of all the lithologic units of the ophiolites. But we noticed the sheeted dikes, when we mapped them, they were all oriented perpendicular to that structural front along which the ophiolite was emplaced. And we surmised that the ophiolite was emplaced with the Notre Dame arc, which is out here, at about 470 million years. And the collision and the abduction was at the same time. Now, you have to realize in the 70s, I was in a department, John Dewey was my supervisor, and people like Jeff Fox and Kevin Burke and Bill Kidd were there whispering in my ear. As soon as you see sheeted dikes, you're at a spreading center. That's it. But then I had Miyashiro, who gave us paired metamorphic belts, but started to work on igneous rocks, and he was whispering in my ear, those rocks are formed in an island arc, and he was writing his papers on Trudeau's. So it was kind of an exciting time. But in 1979, we came out with this paper, Doug Nelson and I, in which we said that the Notre Dame arc, forearc, was the Bay of Islands ophiolite complex, and it was collided, the arc collided and the abduction occurred simultaneously. We also showed that in the arc, with some of the work that John's early work on some of the interarc and suture zone ophiolites, that they were forming probably just prior to collision, like the Bay of Islands we know now. So in 1984, John and I got together and we wrote this paper on initiation of the subduction, but we kind of focused on triple junctions where there were spreading centers in the overlying plate intersecting the trench. And we said that basically you could lengthen the forearc by accreting at these high angle ridges like we were seeing in the Bay of Islands. And we focused on the West Philippine Sea because it had a really high angle ridge, and we thought the forearc of the IBM of the Isobonin-Marianas arc was essentially part of that West Philippine Sea spreading. We also had some other models where the spreading center intersected the relative motion pole and went convergent, and we were migrating poles and creating instantaneous accretion and placing it into convergence across that pole. So these were just some of our early ideas, and we sort of didn't have much geochronology back in those days. I think that slide of the abduction was based on 13 total dates, most of them not so good. And then the geochronology and the IBM arc was almost non-existent except for the spreading anomalies. So we sort of went back in 2011 and kind of looked at this model again, and I think we both became more convinced that it might work. And so the idea is that there's this hot corridor of mantle, that asthenospheric mantle that kisses the trench, and that you start making very long forearc segments by accreting right at the trench line. Now, there's lots of complications with this, but one of the things you can do is you can bring that melting zone right to the trench. In fact, I'll show you cases where within 30 kilometers of the trench, there are volcanoes in the forearc. The other thing you can do is you can make bonanites and adikites, which we see all along the Isobonin-Mariana arc and other arcs that have these high angle spreading ridges to the trench. And if you look at most back arc spreading centers, we usually think of them as parallel to the arc, but if you look closely enough, most of them start intersecting the trench at some point. So if you just take the West Philippine case that we went back over, here's the West Philippine Basin Spreading Center that was active from 54 to 32. The extinct ridge is right here. If we surmise that those age bands are in the forearc, it sort of fits with 50-million-year-old lithosphere dated here, 50-million-year-old lithosphere dated up here, bonanites, same age, up in the north and into the south. And then the complication is there have been two subsequent back arc spreading events, Shikoku Basin, Paris Vela, and then the Mariana from 0 to 5 million years. But each of those ridges has created a gap or an elongation of the arc as well. So our total elongation for just the West Philippine was about 1,780 kilometers, and for the entire spreading system of the Mariana and Shikoku and West Philippines, we got about 3,000 kilometers of arc extension along the trench line. So that's just the ages in these back arcs, and there's the general model. But I think there's a connection here between bonanite forearc volcanism and adikites and ophiolites. Those are the bonanites in ophiolites, and forearcs have been well described. So my colleague has kind of modeled, Johnny Wu, has modeled the growth of the Philippine Sea Plate through time, and you can see that these subduction zones have to lengthen, and so we think they're lengthening by these high-angle ridges into the trenches. So basically, this is just the West Philippine Sea age bands in the front of the arc, 1,780 kilometers of extension. And then you look around the world and you start to see more of these intersections between high-angle ridge, North Fiji Basin, the Lao Basin. They all erupt adacites and bononites. And there's the connection with ophiolites. Even in a main ocean basin like this one, we've now found bononites in the Macquarie case. So triple junctions may be fairly important for generating both arc length and ophiolites. So there's the basic model, and I'll just run through these three sites where we do have these high-angle ridges. The northeast Lao Basin, it basically kisses the trench, and there are adacites and bononites erupting in the last 2.5 million years right here. We know that this part of the Mariana arc is the forearc is 51 million years old from a date on zircons here, and the volcanics here are dated at 2.5 million years across that boundary. So we think all of this material is new seafloor, and you can look at the backscatter data, and the backscatter data shows this bright zone right in through here. So there's where the trench is lengthening at this high-angle intersection between the trench and the back arc. And it may have something to do why Challenger Deep is there as well, but we haven't worked that out. And then the North Fiji Basin, this is a map by Bird. I always like Bird's map because he always draws the ridges right to the trench, whereas most people sort of end the back arc basin somewhere behind the arc. So there's just a picture of the Mariana. And it gets complicated because you can have ridges that are straight and intersect the trench, and that makes it simple, but they can have transforms as well. So you get these pieces of old forearc and new forearc juxtaposed in strange ways. And then if you have a triple junction, like in the North Fiji Basin in the back arc, you get this kind of double swinging barroom doors opening, and you get a new arc material, new forearc right here. So there's lots of different geometries involved in this as well. So I may not have time for the rest of my talk, but here's the Bay of Islands complex. There's the ophiolitic sol. There's a transform kind of at the front edge of the ophiolite. The Bay of Islands ophiolite is younger. It intrudes into that transform. There's an autochthonous relationship between the two. Sheeted dikes clear across the island of Newfoundland into the Notre Dame Arc. You have sheeted dikes that are oriented in this direction, perpendicular to the structural front of emplacement. And that's even through the arc. The ophiolites through the arc have the same orientation right through the arc. These are some of our old maps, hand-drawn, I guess, of the metamorphic sol at the base of the ophiolite. So this is Hartsbrigite Danite transition zone in Gabbro. But basically, we go from rocks that were accreted at 10 kilobars and 900 degrees down to greenschist facies and then into subduction melanges below. And these are what the rocks look like. They're highly deformed, lots of transpulse layering, mixtures of sedimentary rocks and mafic rocks. And they all have the mafic rocks, where we can isolate them, have more Barrow-IB signatures. And all of the ophiolitic rocks have arc signatures associated with them. So these are some of the granulites near the contact. These are the kind of pressures that we get up to about 10 kilobars at the contact with the Hartsbergite, 900 degrees or so up at the contact. And that's pretty common for most ophiolites. So you have a pressure and temperature gradient and a deformation gradient. Let me go through this quickly. So most people, when they talk about subduction, talked about the temperature of the downgoing slab. I'd rather see people model the overriding plate where these intersections occur, because they create the right conditions for shallow melting like bononites and slab melting like adacites that we see along these forearcs with these high angle ridges. And you can really create a lot of real estate in the forearc by having these ridges at a very, very high angle to the subduction complex. Well, I see a red light, so I better quit there.